Welcome back to Linear Circuits. Today we're going to begin our discussion of transformers. This lesson is essentially just going to present transformers as a device and describe the physics behind how they work. This concept of transformers is a fairly extensive one, and so to help make it a little bit easier to learn, it's been broken up into several smaller pieces so that it is nicely compartmentalized. In the previous lesson, we talked about maximal power transfer in AC systems. Sometimes to get maximum power transfer, transformers are actually used for the impedance matching that was discussed. But we're going to talk about transformers generally and look at a number of different places that they turn up and they're used. The objectives for this lesson are to identify physical transformers and their circuit representations, and then to describe the physical function of transformers. This is representative of a transformer. Here, the gray is indicative of a ferrous metal core. So ferrous meaning that it's got some iron in it. And the reason behind it being ferrous is ferrous materials hold magnetic fields very well. Then we have two coiled wires represented in these somewhat orangish colored coils here. So this side, as we put a current through it, is going to generate a magnetic field, according to Ampere's law, which we've already discussed when we talked about inductors. When the magnetic field is established in this coil, because of this ferrous core, it's going to then have an impact on the other coil, since now there's a magnetic field that is moving through this second coil, this second inductor. So when we put them together in this configuration, we call it a transformer. It doesn't necessarily have to be quite like this. The only thing that makes it a transformer is this idea of mutual induction, that current going through one coil generates a magnetic field that has an impact or an effect on the other coil. When we do circuit diagrams, they will be drawn somewhat like this, where we basically have two inductors that are placed side by side, and the dots here are representative of reference directions. The reference directions that are present in transformers are with regard to the directions of these coils. And so it's possible that you could coil this the opposite direction, in which case you would move one dot down to the other side. This lets you know whether this magnetic field is basically working in the same direction or the opposite direction that the magnetic field is coming from the other coil. In these systems, we're typically going to connect one side to a source and the other side to a load. So to help distinguish the two sides of the transformer, we will refer to one side as the primary winding, or the primary, and the other as the secondary winding. And typically the primary winding relates to the winding that is connected to your power source, and the secondary winding is connected to some sort of load. It's entirely possible to flip the direction of the transformer, and then you could then change calling the other the primary, and then the previous one the secondary. It really doesn't particularly matter. It's just to keep things clear as to which side you're referring to. As far as the relationship of magnetic field and current, first of all, we know about Ampere's law. As current flows through the coil, it generates a magnetic field. The other thing that makes these devices operate is Faraday's law of induction. Faraday's law of induction states that a changing magnetic flux leads to a voltage. We're not going to get into the finer details of Faraday's law of induction, but to be able to talk a little bit about it, we need to have some idea of what magnetic flux is. So if we take some sort of closed loop and we make a surface that connects all of the sides of this loop, and then we count the amount of B field, or the magnetic field, that's going through this surface, and then divide it by the area of this surface, that gives us magnetic flux, which is represented by a capital Phi. This is somewhat similar to the way that we calculated current. We calculated the amount of charge that was moving through some surface in time. So it's a similar kind of an idea. Faraday's law of induction states that changing magnetic flux leads to voltages, which means that if the B field here is constant, there's no changing magnetic flux, so zero voltage, which is why inductors behave like wires. If you let the currents flow through them, stay constant in time. So the implication of this is that transformers are AC devices. In order for them to work the way that we've described, you need to have an alternating current. If the current is DC, or if it's constant at time, it doesn't quite have the same impact as it would if the current were alternating. There's two primary models for analyzing transformers in a linear sense. The first is the linear transformer model, where it uses impedances for the analysis, impedances for the two coils, as well as impedance for the mutual induction. This is primarily used in communications applications. The ideal transformer model is primarily used for power transfer applications. It requires a few different assumptions to be made that are never quite actually true, but they generally give us a good idea of how the transformer is going to operate in a certain circumstance. And for ideal transformer models, we're simply going to be making use of the voltages and the number of coil turns for the analysis. To summarize, we just introduced transformers as a circuit device, described their physical behavior, and then introduced the two analysis modes. In the next lesson, we'll start by talking about the first of these, the linear transformer model, to see how we can use it for analysis. Until then.